Hello everyone, welcome to my channel. This is an educational channel where we look at different researchers in the past who have, in my opinion, made great contributions but have not been recognized for doing so. And we delve into their theories and their contributions deeply and try to figure out how to apply them in our own lives, how to benefit from what they've taught, and how to also, promulgate, broadcast more about what they've done, so that the whole world can benefit from their theories, which in general have been squashed by the powers that be out there that are trying to pump up the standard paradigms. And today is our 326th video that we've done on Dewey B. Larson and his reciprocal system of theory. And Mr. Larson was born in 1898. And in about 1930, he started to have some inklings about his reciprocal system. He was, I think, a mining engineer, some kind of engineer, living out in the Northwest and the Portland area. And he was working on kind of the solution to some chemical problems that were quite a bit less revolutionary. But he stumbled across some things and, basically answered the call of, okay, this is going to be a difficult research. You're not going to get recognized for this. Most likely, you might get a lot of grief for it, in fact. But if you work it out over the course of your life, you're going to leave behind some stuff that maybe will last forever. And he did it. And it took him about 30 years to work out his theory on in an inductive manner, to the point where he was able to articulate two fundamental postulates. And from those postulates, he used a process of deduction in order to come up with a theoretical universe from which he wrote his books. And so he's got books on chemistry and astronomy and physics and atomic physics and astrophysics. And he's also got some stuff on economics and on various liberal arts subjects, as well as philosophy, psychology, religion. And his followers have even gone further afield. So he's left an imprint, but not too many people have know where to look or know what it is. And he left his theories in kind of, not a shambles, but you can't really ask too much of a person. He put the information out there. The fact that it's not, widely accessible, I mean, he had to kind of come up with a whole new language to describe it, and he had to overcome the inertia of the standard paradigms and all of the wrong think that we have in our heads. So the hardest part about learning the reciprocal system is unlearning the other stuff, to be open to learning Larson stuff. So it's a hard go, but I think it's worth it. And what we're doing today is we're going to look at an article that he wrote that is called "The Nature of Motion," and this should clarify some things, I think, because the essence of Larson's fundamental postulates and the reciprocal system is that we live in a universe that is composed entirely of motion. Not matter, not energy, but motion. And for Larson, motion was the relationship between space and time. And that implies a reciprocal relationship between space and time. Motion is basically a fraction with time or space as the numerator and space or time as the denominator. Space and time do not have an independent existence, independent existences. They only exist together in motion. And they exist in 3 dimensions each. They have the same qualities, time and space. Not always at the same time, but they both have 3 dimensions. They both have their aspects that are progressing, or Larson calls it clock space and clock time. The clock is always getting later and later and later. Space is always getting farther and farther and farther apart. And Larson refers to that as a scalar motion, because it's a motion that has a magnitude, but it has no specific direction. The clock is always getting later and later and later, but it's not getting later in any specific direction. You can't say it's getting later to the south, or it's not getting later this way, but it is just getting later. And so too with space, it's always getting farther and farther and farther apart, but not in a particular direction. You can envision this by using a balloon with dots on it, and then you blow up the balloon, all the dots are moving away from each other. But they're all moving away from each other. They're not, so it's really encompassing all the directions, not any specific direction. And this was also observed by the Hubble telescope that determined that all of the distant galaxies are moving away from each other. So this scalar motion is a kind of motion that has factual basis. You can point to things that are engaging in scalar motion, but it hasn't really been acknowledged by scientists that this is a different motion in kind than the normal vectorial motion that we're accustomed to. And Larson really builds his system out of this concept of scalar motion. So, and then the other aspect of space and time is that they are both quantized, meaning that they come in chunks, they come in units. They're not infinitesimal. They're not continuous. They come in very small units. If you don't have a full unit of space, then you don't have space at all. If you don't have a full unit of time, then you don't have time at all. And that is more or less is the first postulate and the most important postulate of Larson's 2 postulates. But since he is here just speaking about motion, let's let Larson speak about this topic himself, and we can he goes over, I love how Larson is a good historian of science, and kind of goes through, the basic historical background to this, and then how he fits into it. Okay, so a half-century ago, Percival Bridgman, one of America's foremost scientists, pointed out that many of the basic ideas and concepts to which scientists subscribe, quote, have not been thought through carefully, but are held in the comfortable belief that someone must have examined them at some time, end quote. One of the concepts to which this comment by Bridgman is particularly appropriate is that of motion. Most scientists are apparently willing to go along with Newton's view that motion does not need to be specifically defined because it is, quote, well known to all. But in order to make use of this concept in a scientific context, the rather vague general understanding of its meaning that is well known to all has to be given some more specific significance. The objective of the present discussion is to show that the qualifications that have been added to the layman's definition of motion in the pursuit of greater specificity are too restrictive and lead to misinterpretation of a number of basic physical phenomena. The core of the currently accepted definition is the assertion that motion is a change of position relative to some identifiable object. For present purposes, this statement can be accepted as valid. But present-day physics goes on to assert that in order to define the motion of object A specifically, a frame of reference must be constructed on the reference object B. The location of object A is then specified by a position vector in the reference frame, and its rate of motion is specified by a velocity vector, the time rate of change of the position vector. Any change that can be defined by such a velocity vector is unquestionably a motion. But the point now at issue is whether this definition is comprehensive. That is, are there motions that cannot be defined in this manner? And just to backtrack, in case you're, trying to recall from your high school physics class or whatever, a vector is just a motion in a direction. It's like an arrow, a motion in a direction. So are there motions that cannot be defined in this manner? For an answer to this question, let us look first at the astronomical situation. One of the most important astronomical discoveries of modern times is the recession of the distant galaxies. According to measurements of the Doppler shift in the radiation received from these objects, they are all moving radially outward from our galaxy at high speeds, meaning like as a radius. They're all moving radially outward from our galaxy at high speeds. We cannot measure the motion of our own galaxy, but unless we make the assumption that it is the only stationary object in the universe, an assumption that was repudiated by science long ago, our galaxy is receding from all of the others. That is, it is moving outward in all directions. Okay, so in case your history of science is also rusty, this was the whole idea behind the Copernican revolution. In 1543, Copernicus wrote his book, and while he was on his deathbed, or he put out his book on his deathbed because he knew he was probably going to be put to death if he put it out any time before then. But his book is basically saying that the Earth is not at the center of the universe, and that it was the sun which was at the center, at least of the solar system. Prior to that, it was considered that the Earth was at the center of the universe and everything was basically rotating around Earth. But Copernicus, through improved telescopy and improved measurement, realized that it made a lot more sense from the observations to assume that the sun was at the center and not the Earth, and that all of the heavenly bodies, or at least the planetary bodies, were rotating around the sun, not rotating around the Earth. And the Pope was totally opposed to that idea, and was willing to put people to death, all the popes. Galileo was banished for propagating the same kind of idea. Giordano Bruno was burnt at the stake for doing the same. And it took really 150 years until Newton came along in the late 17th century for kind of the world to come around to actually, you know what, that they're right. The sun is really at the center of things in the solar system, and who knows whether the sun is at the center of the universe or not. Probably not. And so Larson is really saying here, unless we make the assumption that our galaxy is the only stationary galaxy in the universe, an assumption that was repudiated by science long ago, our galaxy is also receding from all the others. Just like all the others are receding from each other, ours is receding too, even though we can't really measure that. And so our galaxy is also moving outward in all directions. And since it is conceded that our galaxy is not unique, it follows that all of the widely separated galaxies are moving radially outward from each other in all directions. Attempts have been made to explain the origin of this motion, the currently favored hypothesis being that it is due to a general expansion of the universe. But it does not seem to have been generally realized that the nature of the motion itself is something that also calls for a more comprehensive understanding. So far as can be determined from the scientific literature, the characteristics of the motions of these distant galaxies have not been subjected to any critical investigation, apparently because it has been assumed that the galactic situation is a special case having no relevance to physical activity as a whole. The error in this assumption is evident when we note that gravitation is clearly the same kind of motion. This is not readily recognizable under all circumstances, but since the basic nature of a physical phenomenon does not change, we can establish the basic nature of gravitation by consideration of an example in which the extraneous factors that tend to confuse the situation are at a minimum. Let us consider a number of galaxies relatively close together, as they are in a cluster, and approximately the same size. We know that since these galaxies are free to move, they will move inward in all directions toward each other at speeds that conform to a uniform pattern. This motion is identical with that of the distant galaxies, except that it is negative. That is, it reduces the separation between the moving objects, whereas the motions of the distant galaxies are positive, increasing the distance. Motion that takes place uniformly in all directions, coincidentally, have no specific inherent direction. It is completely defined by a magnitude, positive or negative. That is, it is a scalar motion. A small scale example of scalar motion can be seen in the motions of spots on the surface of an expanding balloon, often used as an illustration by those who undertake to explain the nature of the galactic motion. In this case, the motion can be reversed. Spots on the surface of a contracting balloon have a negative scalar motion analogous to that of gravitating objects. Whenever a new view of a familiar phenomenon is introduced, there is a general tendency to assume that it is a product of a new theory or hypothesis, and the question as to the validity of that innovation becomes an important issue. It should therefore be emphasized that the existence of scalar motion is a matter of direct observation and is independent of any theory. It is one of those observed facts with which all theories must agree in order to be valid. The previous failure to recognize the existence of this type of motion was not due to any lack of empirical evidence or to any question as to the validity of that evidence. It was purely an oversight, due mainly to the manner in which knowledge in the two physical areas most directly involved has developed. Understanding of gravitation has been developed in terms of force, without a clear recognition of the fact that force, by definition, is a property of motion, a point that will be examined later in this discussion. Meanwhile, the concept of motion as inherently vectorial had remained unchallenged for so long that the deviant characteristic of the galactic motions were not recognized in their true light when discovered. There has been a general realization that the motion of spots on the surface of an expanding balloon is in some way different from the motions of our ordinary experience. It is this realization that has made the use of the balloon for explanatory purposes feasible. But expanding balloons play no significant role in physical activity, and no one has heretofore been sufficiently interested in the physics of these objects to undertake a systematic investigation of the characteristics of their motion. Once it is recognized that gravitation and the recession of the distant galaxies are motions of the same kind, this investigation can no longer be neglected. This finding makes it clear that scalar motion is not something minor and incidental. It is one of the basic features of the physical universe. The characteristics of vectorial motion are defined by Newton's laws of motion and are accurately represented in the conventional reference system. The first law of Newton, which is accepted as a postulate in mechanics, states that an object which is not acted upon by any force moves at a constant speed in a straight line in the reference system. Such a vectorial motion has a specific direction, and if that direction is defined with respect to one location in the reference system, it is thereby defined with respect to all locations in the system. Thus, if object A is moving in the direction AB when observed from point X, it is also moving in the direction AB when observed from another point Y, providing that the observations are accurate in both cases. Coincident vectorial motion at uniform speed in all directions would result in no net movement and no change of position in the reference system. Scalar motion does not conform to these relations. In the example cited, the motions take place coincidentally in all inward or outward directions, contrary to Newton's first law, and result in changes of position in all of these directions. Such motion has no property other than a magnitude. It is simply an increase or decrease in the separation between identifiable points or objects. Thus, it has no inherent relation to the reference system. In order to represent scalar motion in a reference system of the conventional type, a coupling to the reference system independent of the motion must be supplied. The direction of the motion, as seen in the reference system, is a property of the coupling, not a property of the motion itself. Okay, I think we're going to stop there. This article is probably going to take 3 or 4 days to get through. So we're going to find a stopping point right there, and we will start up tomorrow looking at this concept of scalar motion and how it relates to reference systems. Okay, well, thank you for tuning in, and have a great night.